Alright guys, we're going to continue on with the chemistry chapter where we look at the chemical aspects of life. There were some slides left over at the end of part 1 that we did not finish yet, so I just added them to the beginning of this presentation. So we'll go over them right now. We were talking about how atoms can join together to build bigger compounds or bigger molecules. When that happens, when atoms are joining together, that's a chemical reaction, right? Or even when atoms are being broken apart, that's a chemical reaction. When atoms interact with each other. Now, there are all different types of chemical reactions. And we're going to go through a couple of the kind of like key categories of reactions. Decomposition reactions occur when chemical bonds are broken and a large molecule is broken down into two smaller molecules. Just like the word decomposition, right? When something decomposes, it's breaking down. So a decomposition reaction is breaking down a compound or a molecule. These A's and B's, they're just variables. They could be anything, right? A could be hydrogen, B could be carbon, or it could be two glucose molecules, or it doesn't matter. They're just variables. But over here, you see that they're together, right? They're joined together. It's one large thing. And then as the reaction progresses, you see that they get broken apart from each other, and now they're separate. We have A and we have B, two smaller things. The most important kind of decomposition reaction in humans is called hydrolysis. And we'll see hydrolysis reactions happen a lot. It's a really important type of reaction. In hydrolysis, it's decomposition, so we're breaking something down, but we break it down using water. And that's literally what hydrolysis tells us. Hydro means water, and to lyse something means to break it apart. So water breaks apart. That's what hydrolysis literally means. So if you look here, for some reason my eraser is not working, guys. Sorry. I'll stop scribbling then. If you look at the reaction, it has A and B together, right? They're bonded together. And then you see it has water, right? Which is H2O. And then as this progresses, you'll notice that this H2O splits up, right, into hydrogen and OH. And those chemicals come in here, and the hydrogens with the A, the OHs with the B. But the point is, we took this one large thing here and we separated it, right? We broke the bond between those two variables. A synthesis reaction is the opposite. In a synthesis reaction, we make chemical bonds, right? Synthesize, we create a chemical bond. So we're building up something larger. For example, here, A and B are separate, and then as we go forward, you'll notice a bond forms between them, and we form one larger compound. Dehydration synthesis reactions are the most important synthesis reactions in humans. With dehydration synthesis, it's literally the exact opposite of hydrolysis. So with hydrolysis, we added a water to break a bond. With dehydration synthesis, we remove water and form a bond, right? Dehydrate, removing water from something. So we take this, right, two hydrogens and an oxygen, and that gives us water. And then that allows us to form a bond between the two variables, the A and B. So we're forming this chemical bond right here, and we did it by removing a water. So again, hydrolysis and dehydration synthesis are opposites of each other. I'm not super worried about this slide, but an exchange reaction is just when both happen. when you have two compounds and you break them down and then they exchange partners or get kind of mixed up with each other and then you form new bonds. So they exchange partners. And again, this involves decomposition and then synthesis. So here, these things would break down and then switch partners and then form a new bond. And here you see that they've kind of switched around a little bit. Real quick, guys, on these, when we talked about metabolism and anabolism and catabolism, remember that metabolism is all of our chemical reactions. So any of these are included in our metabolism. But catabolism is the chemical reactions that break things down, right? Like a catastrophe. So these chemical reactions here, decomposition reactions, like hydrolysis reactions, those reactions are included in the body's catabolism, right? Reactions that break things down. Synthesis reactions, like dehydration synthesis, those are included in the body's anabolism, right? Remember, anabolism are the reactions where we build things up. Then if you put all this together, right, any of these reactions together, we get metabolism. Okay, so in the body, we've got all these chemical reactions happening all the time, right? Millions of chemical reactions are happening in the body right now. Now, the thing is, those chemical reactions take time. They're kind of slow, and our body doesn't have the time to sit and wait around for all these really slow reactions to happen. We want to speed them up. So we give these reactions a little bit of help to get them going fast so that we can have a nice fast metabolism, fast chemical reactions. In a normal chemical reaction, the activation energy is the amount of energy that's needed to make that reaction happen, right? So the more energy you have to put into the reaction, the slower it is. What enzymes do are enzymes lower the activation energy. Okay, so if you look at this graph right here, without an enzyme, this is energy on the vertical axis. Without an enzyme, we put these reactants together, right? We put a couple things, two things into this reaction, and you have to generate this much energy before it'll go forward and form your product. That's a lot. It takes time for that energy to build up, to happen. If you have an enzyme, then if you look at this smaller graph, you only need this much energy before you can make your product. Okay, so with the enzyme, it's a lot easier to make a chemical reaction happen. Because of that, the reaction happens faster. So enzymes lower the activation energy of reactions. That means that they speed up chemical reactions. Okay, enzymes speed up chemical reactions. They are what we would call catalysts. A catalyst is just anything that speeds up a reaction. Heat, for example, could be a catalyst. When you apply heat to something, sometimes that makes it happen faster. In this case, it's an actual enzyme that we're putting into the reaction to make it happen faster. Water is really important for the human body. Your body is made up of mostly water, and there's a reason for that. You guys saw that water is a polar compound, right? That its H2O has polar covalent bonds. So part of it is kind of positive, part of it is kind of negative. And that really affects the way that water behaves and the way that other atoms behave when you put them in water. Water is an excellent solvent. What that means is that lots of different stuff dissolves in water. So salt dissolves in water, sugar dissolves in water, Again, this is really important that most things dissolve in water because we want them to dissolve in our body. We don't want big chunks and crystals of things inside the body. We want it to be fluid. So water has really great solubility. When we talk about solubility, just to introduce you to the terms, salt water, for example. Water is the solvent and salt would be the solute. Okay, so the solute is the thing that's spread throughout the water or dissolving into the water. Water has great reactivity. It's very reactive, and most body chemistry occurs in water. We just said that a couple of the most important reactions in the human body are hydrolysis and dehydration synthesis. And both of those reactions occur in water, right? Either we put water in or we take water out, but water is necessary in both situations. That's the case for a lot of the chemistry, a lot of the reactions that happen in the body. Water has a high heat capacity. What that means is that water can absorb and release large amounts of heat without changing temperature. So water has a very stable temperature. It's hard to change the temperature of water. What that does, since we're mostly water, that means it's hard to change the temperature of us, of our bodies. We have a very stable temperature. You have to add a whole lot of heat energy to us in order to make our temperature increase. This also allows us to distribute heat throughout the body because we have so much fluid that's constantly moving through the body, like our blood. It's constantly being pumped through the body. It distributes the heat that's present in that blood all throughout our body so that we don't have little pockets of heat. For example, your muscles generate heat, but if you go for a run, your legs aren't really, really hot while the rest of you is really, really cold. The blood flows through those muscles and it takes the heat and then brings it to the rest of the body. So the fact that water holds a lot of heat in it allows it to distribute it throughout our body so that we have nice, even temperature. Finally, water is really great at lubricating surfaces. So most of our tissues and cells, organs are surrounded by water. And this water provides moisture and reduces friction so that we don't damage our tissues as they move. You don't want your organs to be rubbing up against each other like a rug burn, right? You don't want them to get rug burn from rubbing up against each other. So we coat everything in water. And because water is good at lubricating things, it decreases the rub, it decreases the friction so that our tissues don't get damaged. All right, we need to take a second and talk about something called pH. What the pH is technically is a measure of the concentration of hydrogen ions in a solution. So pH correlates with or is related to the amount of hydrogen ions that are present. Technically, if you guys want like the technical definition of it, the pH equals the negative logarithm of hydrogen ion concentration. These little brackets mean concentration. So if you had a solution and you measured the number of the concentration of hydrogen ions and then took the negative logarithm of that number, you would get a number for the pH. Now, the pH scale goes from 0 to 14. So you would get some number that's between 0 and 14, and that would be the pH. Now, the reason we use this pH scale, sorry, I'm trying to think of the easiest way to explain this. the reason we use this pH scale from 0 to 14 is that this is really challenging to deal with. Okay, so for example, if you took water, a cup of water, not very much, but some of this water spontaneously separates into hydrogen and hydroxide. And then it links up back together, and then it separates and links back together. So in a sample of water, there is a little bit of free hydrogen. When we look at it, it is 0.0000001. Okay, hydrogen per, I'm not sure what the units are, hydrogen per milliliter solution. Okay, that number is a pain in the butt to deal with, right? How much hydrogen is in there? 0.0000001. So instead, it's a lot easier to convert that to a number between 0 and 14. Okay, the negative logarithm of this number is 7. So we say that the pH of water is 7. Okay, that happens to be what we call a neutral pH. So pure water has a pH of 7, which is neutral. Okay, it happens to be because it has a balance of hydrogen and hydroxide ions. Okay, but I want you guys to know water has a pH of 7, and that is a neutral pH. I also want you to know that the pH is a number that goes along with the concentration of hydrogen ions. You don't need to know any of this up here. This is just to show you that there are rules behind this. There is science behind this. Now, the pH scale, right, again, that goes from 0 to 14 and has water in the middle at 7. I told you guys that this correlates with the concentration of hydrogen ions. Now, the number on the pH scale has an inverse relationship with hydrogen ion concentration. Inverse is like opposite. Okay, so that means they move in opposite directions. The pH number and the concentration of hydrogen ions go opposite directions from each other. So the more hydrogen ions, the lower the pH number. Okay, the fewer hydrogen ions, the higher the pH number. Now, I have this coming up on the next slide, I believe, but here on the scale, you see pure waters in the middle, right, at a pH of 7. If you look less than that, right, so from 0 to 6.9, that pH is acidic. Okay, those are acids. That is an acidic pH, less than 7. And if you look here, right, the lower the number, the more hydrogen ions. So that means as we move this way on the pH scale, we get more and more and more hydrogen ions. Okay, so the more hydrogen ions, the more acidic, the lower the number on the pH scale. And then the opposite, if we go from 7.1 up to 14, that is basic, right, or alkaline. Now, like we have right here, as we move up and up and up with the pH number, that means we're getting fewer and fewer and fewer hydrogen ions. Again, I just mentioned that an acidic pH is a pH lower than 7, and that acidic things have high hydrogen ion concentrations. Things that are basic or alkaline have a pH higher than 7, and those things have a low hydrogen ion concentration. Now, why do we care, right? The pH of human blood is slightly alkaline. It's slightly basic, just above 7. Human blood should be between 7.35 and 7.45. If it's not in that normal range, there's a disease process present. There's a problem in the body. Those problems are called acidosis or alkalosis. Acidosis is the disease that occurs when the blood is too acidic. So that's when the pH of the blood, so acidosis is when the pH of the blood is too low, so less than 7.35. Right? If it's less than 7.35, it's too acidic. The person has acidosis. Alkalosis is when the blood is too alkaline or basic. So that's when the pH of the blood is greater than 7.45. And these things can happen for multiple different reasons. They can happen when you're not breathing appropriately, when you're not breathing at the right rate and carbon dioxide builds up in your blood. You can end up with acidosis. These can happen because of severe diarrhea, metabolic disturbances. There are numerous things that can cause this. Kidney failure can cause issues with pH. All right, so we are going to completely change gears here. And from here on through the end of tomorrow's lecture, we will talk about organic molecules or organic compounds. Our body is made up mostly of organic compounds or organic molecules. Besides the water, I mean, the actual tissues that we have are made of organic compounds. All organic compounds contain both hydrogen and carbon covalently bonded to each other. If it's organic, it has to have both hydrogen and carbon. Usually there's oxygen as well. Most organic compounds also have oxygen. And then we'll see that like proteins and nucleic acids have a bunch of nitrogen too. But the definition, in order to be defined as organic, it has to have hydrogen and carbon. There's typically like a big bunch of hydrogen and carbon, either in like a long chain where you've got a ton of carbons like this, and then there's hydrogen sticking off of them, or in a ring maybe where you've got carbon, at the corners of these rings, and then there's hydrogen sticking off. There's all different shapes of these like backbones with tons of hydrogen and carbon. But then there's also these little functional groups that stick off of these hydrocarbon chains. And those functional groups are what determine the chemistry or the behavior of the compound. Now, the different types of organic compounds that we'll look at include carbohydrates, like sugars and starches. Lipids, those are like fats, right? Like cholesterol or triglycerides. Proteins, which are made up of chains of amino acids, and then nucleic acids like DNA and RNA. Now we are going to spend the rest of the chapter talking through all of these different types of organic molecules. Remember I told you guys there's like a bunch of hydrogen and carbon, and then there are little functional groups sticking off. This table just tells you some of the functional groups. You don't need to memorize this. I'm not going to quiz you on what the functional groups are. If you go to organic chemistry, you'll learn that. But as we go through the lecture, you might hear me say, a phosphate group or amino group. If you're curious what that actually looks like, you can come back to this slide. This is the carboxyl group, the amino group, hydroxyl, and phosphate. This R variable that you see here, this is just the hydrocarbon part, the part with carbon and hydrogen. All right, so the first organic compound that we're going to start with is the carbohydrate. Carbohydrates, again, include things like sugars and starches. Carbohydrates contain carbon, hydrogen, and oxygen in a 1:2:1 ratio. What that means is for every 1 carbon, there are 2 hydrogen and 1 oxygen. So there should be the same number of carbon and oxygen, and there should be twice as many hydrogen. For example, glucose, which is like the most common sugar that we'll talk about. Glucose, the chemical formula is C6H12O6. That means there are 6 carbon, twice as many hydrogen, and 6 oxygen. Carbohydrates, like sugars and starches, are the primary source of energy for our cells. Our cells use carbohydrates to make fuel, to run the processes that they need to run. Now, our cells can use fats, they can use amino acids, but they prefer to use sugar. Sugar is the easiest thing for the cell to break down for energy. Carbohydrates are classified according to their size. The smallest carbohydrates are monosaccharides. Okay, mono meaning one, because it's a simple sugar with one ring, like one sugar ring. Glucose and fructose are examples of monosaccharide. Disaccharides, di means two. A disaccharide is 2 simple sugars, so 2 rings linked together. And then anything bigger than that, we call it a polysaccharide. Poly meaning many. So many rings linked together gives us a polysaccharide. We'll look at them in more detail right now. So again, a monosaccharide is a simple sugar with 3 to 7 carbon atoms, so one little sugar ring. Classic examples are glucose, fructose, galactose, but again, glucose is the most frequent of these that we'll talk about. Disaccharides are a little bit bigger. Hey, that's when we have 2 simple sugars or 2 sugar rings, and they get linked together, condensed, by a dehydration synthesis reaction. Remember, dehydration synthesis is a chemical reaction where we remove water and we form a bond. So we had 2 sugars that were separate, we performed dehydration synthesis, and we link them together to have one sugar, one disaccharide. Examples include sucrose, maltose, lactose, that's what's in your milk. Now, finally, polysaccharides are really, really large starches, for example, that include many monosaccharides linked together by dehydration synthesis. So every time you link a sugar on, you perform another dehydration synthesis reaction. And this happens to form really large things. So again, starches like we eat in potatoes, those are huge carbohydrates. Glycogen is really important. Glycogen is the way we store extra glucose, extra sugar, in our muscles, in liver. In muscle and our liver. I'll show you what it looks like in one sec. So this is showing us the dehydration synthesis reaction, how we link together 2 sugars to make one larger sugar. So you'll notice here these are separate from each other, right? We have glucose and fructose, right? Each one has the one ring. Okay. These are both monosaccharides, right? Because it's just one ring. Now we're going to link them together to make, over on this side, a disaccharide. We do that via dehydration synthesis, right? We pull out a water, it's in red over here, the molecules will pull out. We pull out a water, and you see that water here, and we form a bond. Here you see, now we have linked together these 2 sugar rings at this oxygen. So we have one larger molecule here, instead of 2 smaller. This is glycogen, the way we store glucose. Now, this is a big, huge molecule, right? This up here is taking just this one little tiny part of it and blowing it up so you can actually see what it is, the atoms that are here. but each little like circle, each one of these tiny circles is showing you a glucose. So we link together a ton of glucose to make one single glycogen. And every time we link another glucose on, it's another dehydration synthesis reaction, right? So there was a dehydration synthesis here to link on this one, and here, and here, and here. Again, we do this when we have tons of sugar. So if you eat a big meal, you've got a bunch of carbohydrates in your blood, your body's going to store them for later. So it converts them to this huge glycogen, and it stores that in the liver and muscles. Then later, say you haven't eaten for like 8 hours and your blood sugar is really low. Well, then we need to get the glucose out of storage. So we come in and we break these bonds to release this glucose and use it. How do you think we break those bonds? Hopefully you said hydrolysis. Remember, that's the opposite of dehydration synthesis. With hydrolysis, we would use water and come in to break the bond to free up that sugar so that we could use it. And these two processes are happening constantly. Every time you eat, we make more glycogen. Then when you haven't eaten for a while, we break down the glycogen. And that's happening all the time. Okay, so that's it for carbohydrates. Now we'll switch gears a little bit and talk about lipids. Lipids are mainly hydrophobic molecules like fats and oils and waxes. Hydrophobic literally means water-fearing. Lipids are water-fearing. Lipids do not like water. They don't want to mix with water. And a reason for that is that they are very different compounds. Lipids are non-polar compounds. They are very balanced. They have no charges at all. And water is a polar compound. And when we talk about things mixing together well, we use the term likes dissolve likes. So like things dissolve in like things. These are not like, they are opposite. So lipids do not dissolve in water. They don't like the water. They try and get away from the water. They don't spread out in it. And I'm sure you've all seen this before. If you've seen oil in water, if you've never seen it, go home, or hopefully you're at home, staying safe right now. Take some oil and pour it into your water, and you'll see the oil all like clusters together at the top. The oil forms one big circle, one big group to try and get away from the water. They do not mix well because lipids, like fats and oils, are hydrophobic. Lipids have way less oxygen than the sugars do, carbohydrates. So lipids are made mostly of carbon and hydrogen. They have really long hydrocarbon chains. They're used for many different things. They are used as structural components of cells. Lipids, we'll see, make up the plasma membrane or outer barrier of our cells. We use them for energy and energy reserves. I just told you guys that our body likes to use sugar for energy, but if there's not enough sugar, it will use lipids. It can do that as well. And then also some hormones are also lipids. The steroid hormones are lipids. Different types of lipids include the fatty acids. These are the ones that we use for energy. We actually burn these ones for energy. Triglycerides, these are how we store energy. Steroids, we use steroids to direct different processes and control the body. And then phospholipids, these are the ones that are making up the cell membrane. So we'll start by mentioning triglycerides. Really quick, on the last slide, I told you guys that fatty acids are the fats that we use for energy. Our cells break them down to make fuel. Now, just like with sugars, remember I said when we have a ton of sugar, we link it all together and make glycogen, and then we store it away for later. Well, we do the same thing with fat. When we have a lot of fat, we want to build a bigger molecule and then store it away for later. But the thing about fatty acids is that we can't link them directly to each other like we did with glucose. That doesn't work. So instead, we form something called a triglyceride. And then the triglyceride is how we actually store the fats or store the energy. Okay, so down here where it says energy source, I want you to cross that out and write store, okay, or energy storage, because it's actually the free fatty acid that we're using for energy. So what is a triglyceride? A triglyceride is 3 fatty acids attached to a glycerol. So it's like there's this molecule called a glycerol that's this head region, and then there are 3 fatty acid tails. That's how we take these individual fatty acids and create a bigger molecule that we can store in the body for later. So functions, triglycerides we use for energy storage. They do provide insulation and protection for the body. That's why like animals that live in the really cold Arctic have a lot of fat, right? That fat insulates the body to help keep the warmth in. And then really delicate areas often have extra fat present to protect them. Here you see the way that we form a triglyceride. So up here, up top, these are all separate molecules. So there's a glycerol right here, and then there are fatty acids. There's 1, 2, 3 fatty acids. Now, these fatty acids can be used for energy, but if we've just eaten a meal and we've got tons of sugar available, the cells are going to use sugar because it's easier to break down. And we'll just store this fat away for later because we might need it for energy later. So if we're going to store these fats, we can't store them like this. We want to make a bigger molecule for storage. So we have to take these separate fatty acids and convert them into a triglyceride. The way we do that is with dehydration synthesis. Told you guys, these are the reactions we see over and over in the body: dehydration, synthesis, and hydrolysis. So when we've eaten a meal, we've got plenty of nutrients, we want to store these, we'll do 3 dehydration synthesis reactions, right? We'll pull out this water, form a bond, pull out water, form a bond, pull out water, form a bond, right? You see the 3 waters we pulled out, and then you see the bonds that we formed. Now this whole thing is all connected, and that's a triglyceride. Say a bunch of time goes by and you've decided to diet and you're barely eating any carbs. Now your body says, whoa, I need something for fuel, so I'm going to start breaking down these fats. Well, the way that it frees up these fatty acids is by hydrolysis. So in that case, the water comes in and breaks the bond, and you end up with a free fatty acid. It's not attached to anything, and then you can use that for fuel. Same thing with all of these. Another water comes in and breaks that bond. Another water comes in and breaks that bond. Okay, so we form the triglyceride with dehydration synthesis. We break it down with hydrolysis. I'm going to go ahead and stop there. My goal was to get halfway through this presentation, and we are exactly halfway through right now. And phospholipids are really important, so I want you guys to be like super fresh and ready to go when we start phospholipids next time. So you guys are getting off with a pretty short and easy lecture today and tomorrow. So take advantage of it and study a lot. And I'll talk to you guys tomorrow. Bye.